All right, we're in the process of talking about some basic properties of, in particular, convergent sequences. For example, the limit of a sequence, a convergent sequence, is unique. Now we're going to talk about boundedness, and then once we have these properties, we can start doing things with limits, combining them in certain ways, doing arithmetic with them. That's what we're aiming for. So this is on bounded sequences. All right, so what are we talking about when we talk about bounded sequences? Here's a definition. So a sequence, say a sub n, from n equals 1 to infinity, we say is bounded if there exists some number m such that the absolute value of a sub n is less than or equal to m for all n greater than or equal to 1. Okay, so the absolute value of every term in the sequence is at most capital M. That's what we're saying here. Okay, so here's a little example, right, of a bounded sequence. Let's see. Oh yeah, a sub n equals 1 over n is bounded. Why? So let's talk about how we know this. Because there's two things I want to say. One is that 1 over n is positive for n at least 1. Okay. That's one thing. So we know there's a lower bound, meaning 0. So none of the terms go below 0. And then also the sequence is decreasing. Right? And I know this because if I look at sort of 1 over n plus 1, that's smaller than 1 over n. So as you go further out in the sequence, as n increases, then you get a smaller term. For n greater than or equal to 1. Okay, so what these things tell us is that a sub 1, which equals 1, is the greatest term in the sequence, right? The first term is the greatest term because everything afterwards is smaller. It's decreasing. That's what the decreasing part tells us. So this is the greatest term in the sequence. And no term is every term is greater than 0. And every term is greater than 0. So we have this. And that means the absolute value of every term in the sequence is at most 1. So that's our capital M right there. All right, so that's what it means for a sequence to be bounded. There's an example of a bounded sequence. Certainly, you know others and can think of others. So, maybe it's helpful to try to come up with some more examples of bounded sequences and how you know they're bounded. All right, here's a handy fact about just numbers in general that we want to make use of. So this theorem is known as the triangle inequality. And you may have used it and seen it in other places, but it's good to record here. So let's say that x and y are real numbers, so x and y are in R. Then their absolute value, the absolute value of their sum is less than or equal to the sum of their absolute values. Right? You can test this out, play around with a couple examples. It's certainly always true. Sometimes you get equality. Think about when you get that. But certainly the absolute value of the sum is no more than absolute value x plus absolute value y. So I would like to leave this as an exercise for you to prove. You can do it by cases. I mean, there's sort of some quicker ways to do it that I think are less intuitive. or well, I don't know. I guess that's a personal view, but certainly you can do it by cases by thinking about what happens if x and y are both positive or both negative. What if they're different sign? So prove the triangle inequality. Okay. So what I want to use the triangle inequality for here is to prove that if a sequence converges, it definitely has to be bounded. Okay, and it comes up, we'll use it again. So we'll use it again very soon. So here's the theorem. If AN converges, then it is bounded. All right, so let's work on this proof. How is this going to go? So I need to find a bound. That's what we're saying here. If AN converges, that means we can get some sort of closeness to its limit, right? And so that's good, because once you're within a certain range of the limit, you can kind of use that to develop a bound. But then the closeness only occurs after a certain point, so we have to deal with sort of what happens before that too. Okay, so this is going to happen in two parts. We're going to talk about what we can say once we get within a certain range of the limit, and then we'll talk about how to deal with anything else that came before we got close enough. All right, so let's see. Let's say that n equals 1 to infinity, converges to the limit L. Okay, then I'm just going to pick an epsilon. So this is the thing. Once you have a convergent sequence, you can choose any epsilon you want, and then you can say something about it. Okay, so I'm just choosing epsilon equals 1, but literally you can choose any positive value here. Then for epsilon equals 1, there exists capital N such that little n greater than capital N implies that AN minus L is less than 1, right? Less than epsilon. Okay, so what does this tell us? This means that minus 1 is less than AN minus L, which is less than 1. And now add L to all the parts to get L minus 1 is less than AN is less than L plus 1. Again, this is all dependent on N being greater than capital N. So just a reminder for ourselves there. Again, this is sort of the two parts. So we're going to talk about a bound for all of these terms that occur after capital N, and then we'll talk about what happens before that. All right. So this is where the triangle inequality comes into play. So in this case, we can use the triangle inequality inequality to get the following. The absolute value of A sub n is going to be less than the absolute value of L plus 1. Okay, I'm going to leave this for you to work out the details here. That'll be an exercise that I'll put right after we finish the proof. Okay, so the triangle inequality shows that absolute value A sub n is less than absolute value L plus 1. Oh, whoops, specifically, this is for little n greater than capital N. So what about everything that comes before that? Right, that's the question. So that's what we'll deal with in the second part of this proof. But we can certainly bound all the terms that come after capital N in the sequence. All right, so let's continue this proof here. Okay, so there are only finitely many preceding terms. Right? We know what happens after capital N. What happens before that? Well, there are only finitely many terms to consider. So what are the terms? Just A1, A2, and so on, up to A sub capital N, right? We know what happens after this. Okay, that actually makes life a lot easier for us. When there are infinitely many terms, things can be complicated, but with finitely many terms, life is really quite simple. So what I'm going to do here is say the following. Let capital M be the maximum value in this finite set. Oh, whoops, not just plain A sub 1. I want absolute value A sub 1, absolute value A sub 2, all the way to absolute value A sub N, and then also include in this set absolute value of L plus 1. Right. So, all the terms that come after capital N, they're all less than or equal to, or is definitely less than capital L, absolute value of L plus 1. And so they'll be less than the maximum number that comes out of this set. Every term that comes before that, right, A1 through A capital N, in absolute value is less than or equal to one of the numbers in this set. So again, they will also all be less than or equal to the maximum picked out of this set. So we have the following. Whatever n is, it has to be the case that absolute value of A sub n is less than or equal to m for all n, little n, greater than or equal to 1. Okay, so we were able to put a bound on all the terms that came after capital N. Once you have finitely many terms, you can just say, well, just pick the biggest one, and that's a bound for all of those terms, and then we pick the largest out of that, and that's a bound for everything. Okay, so that finishes our proof that if we have a convergent sequence, it has to be bounded. So thus, A sub n is bounded. Fantastic. Okay, great. So here's this little exercise that I would like you to think about again. Involving the triangle inequality, and all, it involves thinking about sort of absolute values as well in some more detail. So I'm just going to let L be some real number, and I want you to show that if x is between L minus 1 and L plus 1, then the absolute value of x is less than absolute value L plus 1. All right, so go ahead and try that out, and then we can, of course, talk about it.